used density yesterday in lab, right? You all did some calculations with density. Why is density useful? What is density? How do you define it? I saw lots of people using it correctly, so you must have some idea of what it is. Anybody want to venture a definition? Yeah. Yeah, how much matter is in a certain amount of space? How much stuff takes up a certain amount of space? So we can write that here. We can roughly define density as the amount of matter in a given amount of space. So how much space does a certain amount of matter take up? Mathematically, what's the relationship of density? If you wanted to make a little equation for it, what would that look like? Yeah, what is it? M over V, right. So if we did that in words, we could say density equals mass over volume. So a certain amount of mass per a certain amount of volume. Whenever we see a relationship like that, per a certain amount of volume. And what units do we usually see density in? You know, like yesterday when we were looking at the density of water, it was 0.99 something depending on temperature. What units were that in? Yeah. Grams per milliliter, right. So how many grams are in 1 milliliter? Another way you'll see that written is grams per cubic centimeter. So that's true for most like smaller things. When we get into gases, we'll sometimes see it in grams per liter because gases are so low density that grams per milliliter becomes a really, really small number. So we do grams per meter instead, or grams per liter instead. And then if you look in bigger scales, like engineering type stuff, you might see kilograms per liter, which is actually the same thing, just multiply 1,000 on top and bottom. So it's actually the same unit. What would be a measure of density in the English or imperial system, not the metric system? What's a measure? What measure do we use for mass in the English system usually? Mass. Pounds, although pounds is actually technically a weight, not a mass, but we would say pounds. So pounds per what? What kind of volume? Yeah, so pounds per, it would have to be cubic because it's a volume. So it could be pounds per cubic inch, or pounds per cubic foot, or pounds per gallon, something like that. Okay. So density tells us how kind of heavy something is, or how much mass is in a given amount of space. So why does ice float? How could you answer that question using the word density? Yeah. Right, ice is less dense than water. Ice is less dense than water. There's less mass in the same amount of space for ice as for water. So what takes up the rest of the space in ice? This is kind of a weird question. We could say this really about anything. What makes carbon less dense than lead? What else is in there? Yeah. It's actually nothing. There's more protons and neutrons in lead, in the same amount of space of lead as in carbon. But we often think about the extra space as being filled by air, like ice is less dense because it has air in it. It's actually not true. It just has empty space in it, literally nothingness. So it's kind of we don't often think about that, but it's true. When we talk about atomic structure, we'll see that actually most of matter is nothing. It's nothingness. It's simply space. So we'll get into that. Anybody ever tested your coolant in your car radiators? Right here? No? Do you know what happens to it over time? Do you ever have to change the coolant in your radiator in your car? You do, or you should. Okay, so now you learned something. So your car doesn't overheat in the middle of summer when it's like 100 degrees. So what you can do, what's ethylene glycol? You know what that is? What's another name for that? It's the stuff that you put in the radiator. No mechanics in here? Coolant or antifreeze is another name for it. Have you heard that term, antifreeze? It's poisonous. You shouldn't drink it. It's really dangerous to animals because if it leaks, it's actually really sweet tasting, and so they'll eat it up and then get poisoned from that. So you gotta watch it. But you put a mixture of ethylene glycol and water, and sometimes some other things too, in this fluid that goes in your car radiator. Why would you put that in there? Right, so the water doesn't boil. Because the car is actually, or the water that goes through your engine to cool it is going to get much hotter than the boiling point of water. And you don't want that water to boil because have you ever seen that on the side of the road, like a bunch of steam coming out of an engine in the middle of summer because something got overheated? That's what happens sometimes. So you put this ethylene glycol in instead. Ethylene glycol has a much higher boiling point, so it doesn't do that. And then also, because it's called antifreeze, it has a much lower boiling or lower freezing point. So it's not going to freeze solid in the winter. And that's why we don't just use water in our engines, we use this stuff. So it's important to maintain the appropriate ethylene glycol to water ratio because sometimes that can break down over time. And what you can do is you can take a little sample out and you can test the density. And the range of density tells you how much ethylene glycol is in there. There's a little device, I don't know if you've ever seen it. It's got a little like bulb on top and a little tube, and you can stick it down in your radiator, suck up a little bit, and there's a little ball inside, and depending on where the ball floats, that gives you the density of the coolant water mixture, and then you can know if it's still good or not. So pick one of those up next time you're at AutoZone or whatever, and check your coolant so you don't get stranded somewhere with an overheated car. Okay, so let's look at how we can work on density in some problems, or use density to help us work on some problems. I really want you to think of density as a conversion factor. All right? It's not a unit factor exactly. It's not like saying one of these is 1 centimeter or 1 inch is 2.54 centimeters. It's not exactly the same as that, but we can treat it like that. So we can use it inside these problems without having to just memorize weird rules about when you're supposed to divide and when you're supposed to multiply. And I think that's one of people's biggest issues with density is sometimes it's hard to keep straight. Like yesterday, I think pretty much everybody encountered this when you were doing your calculations from the experiment. There was a sense of like, wait, do I multiply by the density or do I divide by the density? And there was this question that was often a confusion of when do I do which one? If you treat it as a conversion factor and you follow the units in that factor and label method, then you don't have to worry about that. So let's try it in this problem. We've got 10 mLs of ethylene glycol, and we want to know the mass. So we need a factor that relates volume to mass, and that factor is density. We also know that a cubic centimeter is the same as a milliliter. So we don't have to do a separate conversion for volume. So we've got 10 mLs, and then we want to multiply that by a factor that has ml on the bottom so that they cancel, right? We talked about this on Tuesday. And then a mass on top, in this case, grams. And density gives us that conversion factor. So if you follow the units and you write the units down first, you don't have to think about whether you're supposed to multiply or divide. You just put the units down, put the numbers where they go, and then figure it out just as if you were converting between millimeters and inches or whatever it is. Okay. So now we know that density is 1.132 grams per centimeter, or grams per cubic centimeter. Whoops, 1.1132 grams per milliliter. And that can give us grams. And we probably should have given ourselves a couple extra significant figures here when I wrote this problem down. So we'll call it 10.0 milliliters instead. So 10.0 milliliters times that. We should not need a calculator to determine that that's going to be 1.11 gram, or 11.1 grams of ethylene glycol. See how that works? Okay. So here's a problem from the book. This is a big problem. This is one of those big challenge problems that's supposed to be so tricky and big word problems that everybody hates. So let's go through it together and talk about how we can use density to go through and figure out this type of a problem. So first of all, don't get scared off by the fact that there's a bunch of words. Let's pull out the important information, figure out what we need. Liquid nitrogen has a density of 0.808 grams per milliliter and boils at 77 K. We buy it in a big 175 liter tank. Okay. So we got a big, giant 175 liter tank of liquid nitrogen. We have one of those. I'll show you it later when we do that kind of stuff. The liquid vaporizes quickly to gaseous nitrogen density of 1.15 grams per liter. And we'll talk about STP. Anybody know what that is? We'll get to that in the gas chapter, but anybody know what that means from previous classes? Standard temperature and pressure. There's a 0 degrees C and 1 atmosphere. Anyway, don't need to know that for this question. That's later. The liquid is removed from the tank. Suppose that it all accidentally vaporizes in a room of that size. That's a very small room, so a closet or something, right? Oh no, that's meters. It's not that small. It's like a normal size room. Okay. What is the maximum fraction of the air in the room that could be displaced by the gaseous nitrogen? So this is a kind of a safety type question. One of the dangers of liquid nitrogen is if it all evaporates and becomes nitrogen gas, it could quickly fill a room with nitrogen gas, which is not poisonous to us, but it would displace all the oxygen and then we couldn't breathe. So there are rules like you never take liquid nitrogen in an elevator, for instance, because if it were to evaporate, it could fill the elevator with nitrogen, push out the oxygen, and then you couldn't breathe, and that kind of stuff. So it always has to be kept in rooms that have enough ventilation and stuff like that. So, so we want to do a problem to actually figure out how much of the air in a room would be displaced by a whole tank of liquid nitrogen evaporating. And we can do that by converting some units. So does anybody have a sense of how we start here? What is our starting quantity of liquid nitrogen? Yeah, I heard it. Somebody said it.
175 liters.
Yeah, 175 liters. So we've got this full tank. So it means we have 175 liters of liquid nitrogen. Okay. And liquid nitrogen has a density of 0.808 grams per milliliter. So we might just to kind of keep our accounting here, let's list some of those numbers. The density of the liquid nitrogen is 0.808 grams per milliliter. And the density of gaseous nitrogen, which we'll just say N2 without the L, is 1.15 grams per liter. So different units here, keep that in mind. The liquid nitrogen is given, the density is given in grams per milliliter. The gaseous nitrogen is given in grams per liter. So we want to know how much space liquid nitrogen would take up if it all becomes gaseous nitrogen. Which means we need to convert 175 liters of liquid nitrogen to however much gaseous nitrogen that would be, and that means we need mass. Because it's the same amount of nitrogen, whether it's liquid or gas, it's going to be the same mass, it's just changing its state, and so it's going to change its volume. So how would we figure out how much mass of liquid nitrogen we have in those 175 liters? Well, this is where we have to make sure to follow our units. So yes, we're going to use the density, but we have to keep track of all the units. So we're going to take 175 liters and we want to multiply it by the density, but the density is in grams per milliliter. Grams per milliliter. So what do we have to do over here first with that 175 liters? What? Convert it to milliliters. So we know that conversion factor is going to be, we want liters on the bottom and milliliters on the top. So we get rid of liters and we have milliliters. And then we know that there are 1,000 milliliters in 1 liter. Okay. Now we've canceled liters. So we can make grams out of milliliters. Right? Cancel milliliters, and we end up with grams, and that's where we can use the density and multiply by the density. Because there are 0.808 grams in 1 milliliter of liquid nitrogen. Okay, so now we can multiply all that out. And how many significant figures are we going to use here? Three. We're going to use 3 for this calculation. So that will give us 141,000 grams of nitrogen. If I did that multiplication correctly. Yeah. Okay, another way we might write that, just to make our significant figures clear, would be in scientific notation. So what would that number be in scientific notation? Yeah, 1.41 times 10 to the 5th. So that in a large number like this, we might write 1.41 times 10 to the 5th. Okay, same number. All right. So now what do we have to do? What is our ultimate goal here? What are we trying to find?
Maximum fraction of the air.
The maximum fraction of the air. So we need to know how much space 141,000 grams of nitrogen would take up if it were a gas. How do we figure that? What kind of a quantity are we going to use if we want to know how much space something takes up? Well, that's the volume, yes. So how are we going to get to that from a mass? Right, we're going to use density again. So whenever we want to know how much space a given mass takes up, that's where we use density. Okay, so we'll do another conversion here. And we'll take our 141,000 grams of nitrogen. And again, we're not going to talk about whether we multiply or divide by the density. We're going to just use our units and then figure out what goes where. In this case, we're going to have grams on the bottom because we want to cancel the grams and end up with a volume, which in this case actually is going to be liters, right? Right there. And so grams per liter is 1.15. So in this case, it's a division. But again, we didn't have to know that. We didn't have to memorize that we divide by the density. We just had to put our units in the right place to know that grams are going to cancel, and we're left with liters. So that's going to be 123,000 liters of nitrogen. Okay. So now we know how much space that nitrogen takes up. What do we do with that to finish answering the question? Subtract it from the total. What is the total? Yeah, the volume of air in the room. So how do we find that? The what? The volume of the room. We're going to assume that it's just all filled with air. So there's nothing in the room, right? How do we find the volume of the room?
Multiply all the dimensions together.
Yeah, multiply the dimensions together. So you've got 10 meters by 10 meters by 2.5 meters. That's a cube, or it's not a cube, but a rectangular prism. And so we multiply all the dimensions to get the area. So 10 meters times 10 meters times 2.50 meters is 250 cubic meters, right? So it's just 250 minus 123,000? Or not? Probably not, right? Why not? What's the problem here? Yeah, cubic meter is not the same as a liter. So what are we going to do about that?
Convert it to centimeters, then to milliliters.
Yeah, we could try centimeters and then just do it all by milliliters if we didn't know the conversions, right? In a real world situation, we would probably look up how many cubic meters are in a liter, right? And we just do the conversion that way. Since we don't have that, and let's say you're on an exam and we don't have that number and you got to figure out some way to get it anyway. So maybe we can use something that we know, like centimeters. So we can easily convert from meters to centimeters. What if we recalculate the room volume all in centimeters to get cubic centimeters? So that would be 100.0 centimeters times 100.0 centimeters times 25.0 centimeters. Whoops, no, that's not true. That's not correct. That again, because there's 100 centimeters per meter, right? So let's try 1,000 centimeters times 1,000 centimeters times 250 centimeters. We multiply that all out. That's a pretty big number, so we definitely want to use scientific notation for that. It's going to be 2.50 times 10 to the 8th cubic centimeters. And then we can convert our 123,000 liters into cubic centimeters as well. So we can say 123,000 liters times something that converts cubic centimeters to liters. How many cubic centimeters are in a liter? 1,000, because it's the same as a milliliter. Our liters cancel, and we end up with 1.23 times 10 to the 8th cubic centimeters. Okay, so we've got this number. That's the air in the room. And then we find this number, which is the volume of nitrogen gas that's come out of the cylinder. And the question is, what is the maximum fraction of air in the room that could be displaced by the N2? So what's the relationship between those two numbers, approximately? What's the fraction? Yeah, about half. It comes out to, yeah, with significant figures, it's just about a half. So it would, that amount of nitrogen, liquid nitrogen in one of those big tanks, if it all came out, turned into gas in a 10 by 10 by 2.5 room, it would get rid of half the air. So you'd have half the air gone or displaced by the nitrogen. All right? So that's a tough one. But you'll notice we didn't do anything trickier than converting some units back and forth. We took 175 liters. We turned it into grams. And then we turned the grams into liters of gaseous nitrogen using a different density. All right, then we calculated the volume of the room and we just compared those two. So please practice problems like this. The book does a pretty nice job of stepping up to this. So it'll give you some easier density, some more straightforward density problems first. You get through those, and this one comes in at number 127. So you got 120 some problems under your belt before you get to this one. All right. Let's before we get into matter, let's look at some other problems of this type. So I'm going to pull up some of these problems from the book. And we'll work on that. I'm going to give you a conversion factor for this one. Let's look at number 72 right here. Human fat has a density of 0.918 grams per cubic centimeter. So would that mean that would it float or sink in water? Float, yeah. How much volume is gained by a person who gains 10 pounds of pure fat? So how much more space do you take up if you gain 10 pounds of pure fat? Okay, to do this, we're going to need a conversion between grams and pounds. Anybody know what that is? You know that number offhand? You don't have to know these numbers, by the way. You do have to know the metric conversions, but conversions between systems, you'll be given those numbers. The book has a handy chart of them in the back cover. So we can look for mass and see that 1 pound is 453.59 grams. And that is not an exact thing. So that is with those significant figures. So 1 pound is, I already forgot that number that I just said, 453.59. I'm just going to retype that question here while we flipping back and forth. What was it? How much volume is gained by a person gains 10 pounds of fat? The density of fat is 0.918 grams per cubic centimeter. All right, think you can get that one? Give it a try. A couple more minutes to finish that up, and then we'll see what we get. All right, feel good about this one? I want to throw out some numbers. How much volume did you get? Doesn't have to be right. 4,168 milliliters. Just 168? Whoops, I erased my thing, sorry, hold on. Okay, 4,164 milliliters. Did I get anything different? Everybody got that? Is that how the answer should be reported in significant figures? Maybe. No one wants to.
416.3.9.
Well, how many significant figures should we report in that answer based on the question? Why 5? Because there's 5 up here in the conversion factor. All right, is there anything less than 5 significant figures wise that we're using here? The 10.0. Right, everybody see that? How many significant figures in that one? Just 3. So we should report this answer with 3 significant figures, which would be 4160 milliliters. Yep. I suppose cubic centimeters, although those are the same quantity. Right, 1 cubic centimeter is 1 milliliter. What does the question say? Oh, it says to report it in cubic centimeters. So yeah, we should report that in cubic centimeters. Thank you. Okay, do you want to step through it, or did it make sense?
I don't get the part where you
Let's go through it.
take 4164 and turn it to 4160.
Okay, let's go through it. Probably have some other questions too. So we're going to start with that 10.0 pounds. And we ultimately want a volume in cubic centimeters. So we're first going to step into from pounds to grams, and then from grams to cubic centimeters using the density. So pounds to grams. We got that conversion from the book. And we put the 1 by the pounds and the 453.59 in the grams. That cancels pounds and leaves grams. And then we want to go from grams to cubic centimeters. And for that, we use the density. So 0.918 grams per cubic centimeter. So that means to calculate that out, we're going to multiply 10 by 453.59 and then divide by 0.918 and get, let's say, 4163.9 something. And since pounds canceled here, grams canceled here, we're left with cubic centimeters. All right, so now we have to analyze our significant figures. In the question here, we have our lowest, this is all multiplication, so we're going to use the multiplication rule where we find the lowest number of significant figures, which is right there. It's actually also in our density. 3 significant figures. And that means that we need to round our answer so that it also only has 3 significant figures. Yeah?
Can you try to put it on the calculator because I'm getting 4941.
I'm getting that too.
Oh, okay. Well, you guys gotta tell me if you're getting something different. I don't actually know the answers, so yeah. What are y'all getting? 4941. Okay, let's correct that then. That's seems better. Seems to work better. Okay. So same rule with the significant figures. We need to see that our smallest number, or our number with the fewest significant figures, has 3. Also, the density here has 3. And so that means that our answer can't have more than 3 significant figures. That would be these 3. So those 3 are significant. That 1 is not significant, so that needs to round off and go away. So we should report this answer as 4940. Or to be really, really clear, so we know that 0 is not significant, 4.94 times 10 to the 3rd. Do you see how that rounding works? No. All right. Great. So, yeah.
Quick question, for significant figures, should you do them step by step or just at the end?
Just at the end. Okay. Just at the end. Assuming, let me change that a little bit. If you have a big string of multiplication and division, you do it at the end. If there is addition or subtraction involved, you have to do it separately because the addition and subtraction rules are different. So yeah, as long as there's a whole string, you do it all together and then you do the significant figures at the end. If you do it too early, you're actually losing, you can lose precision and you can end up not having the right rounding. But you should be really close, but yeah. Other questions about this? Okay, there are a bunch of other problems like this in the book, and then they get a little bit tougher and a little bit trickier. Some of the trickier things in the book, and I want to go through one more here, just to kind of give you a sense of what you do or do not need to know for a quiz or an exam. If you go on to the next set of problems, which they call the cumulative problems, that just means they're bringing other things all in together. Let's look at this number 118. A solid aluminum sphere has a mass of 85 grams. Use the density of aluminum to find the radius of the sphere in inches. So we've got an aluminum sphere that weighs 85 grams. And the question is asking us, what's the radius of that sphere? So this is number 118, by the way. Should write this down. 118. Okay. What's the radius of the sphere? Now we need a whole bunch more information. Not a whole bunch. We need like 2 things more than is what is given here. So one is we need to find the density of aluminum. And that's not a number that you would know necessarily. We'll look that up. If we look in chapter 1, I believe there's a table of densities, so you can get a sense of what different densities are. Yeah, it's on page 19, table 1.4. Tells us that the density of aluminum is 2.70 grams per cubic centimeter at 20 degrees C. Another thing that we noticed yesterday, density changes with temperature. So when you look up density, it'll often be given at a particular temperature. For the purpose of our problems, we'll just assume that whatever we have is at that temperature. But when we're doing careful measurements, like in lab yesterday, we'll get the temperature appropriate densities. So density of aluminum is 2.7 grams per centimeter. What else are you going to need to know to be able to solve this problem? The volume of a sphere. And that's something that I would say is not required knowledge in a chemistry class. Maybe you remember it from geometry, maybe you don't. But that's something that I would give you if you needed to calculate that. Anybody know what it is offhand? You remember those formulas? What? Yeah, 4/3 pi r cubed. And actually in the book, it's given a couple problems up in 114 when they start talking about these things. So the volume of a sphere is 4/3 pi r cubed. Now we should have enough information because we've got density, which will allow us to convert from mass to volume. And then we can solve for the radius once we have that volume. So let's do that. We can just do this one together. So we've got 85 grams. And then we're going to convert from grams to centimeters cubed or milliliters. Would that aluminum sphere sink or float in water? It would sink, right? More dense. All right. I don't actually have a calculator. Somebody want to type that out for me?
Calculator?
Mm-hmm.
What is this?
Go ahead. You do it. Just tell me what you get. 31.48. Which we would report as 31, based on 2 significant figures that we have in our the 2 significant figures that we have in our initial mass. And then we solve for the radius. Here's a different color here. So, okay, you solve for the radius. My computer has decided it's working too hard. It needs a little break. Okay. So 31 cubic centimeters is the volume. And so if we solve for the radius, that means we're going to multiply that 31 by 3/4, divide by pi, and then take the cube root So what do you get there? I'll put it up formulaically here. So this is going to be 3/4. Hold on, let me give a little more room here. 3/4 times 31 divided by pi and the cube root of that whole thing. What do you get? .9. And what are the units going to be there? Centimeters, right? Because it was centimeters cubed for the volume. Okay. So an aluminum sphere about that big weighs about 85 grams if it's solid all the way through. It's about 2 centimeters, a little less than an inch radius. That's what that tells us. So let's talk about what you would or would not need to know on an exam or a quiz in terms of this problem. So you would not need to know the density of aluminum. That would always be given, you know, the density of an object. You should know that the density of water is about 1, but other densities you'll always be given. You would not need to know the volume of a sphere, 4/3 pi r cubed. That would be given if you needed that. But you would need to know how to do this kind of algebraic manipulation to solve for r in a problem like that. So that's what you could be expected on a quiz or exam, that you'd be given those quantities and that sort of equation for volume, and then you'd be able to do the algebra to figure it out.
Do you need to have the temperature conversion memorized?
Yes, good point. You do need the temperature conversions. Yes, those are important because we'll use those a lot as we go on, so we'll want to have those ready to go. Please do memorize those. Okay, questions about that? Okay, the next thing we're going to do is talk a little bit about classification of matter, and then we'll take a little break and come back and get into atoms and masses and that sort of fun stuff. Let's look at the 3 states of matter. Have you heard of these before? I hope. Everybody's heard of gas, liquid, and solid? Okay. That may be the case, but you may not have heard of it in terms of these specific definitions. If somebody said to you, what is the difference between a solid and a liquid? You may not know to say, well, a solid has a fixed volume and a fixed shape. A liquid has a fixed volume, but it takes the shape of its container. That's actually the difference between a solid and a liquid. You might say something like, well, a liquid is wet, or like a liquid kind of flows and a solid doesn't. And those are true, but that's not really a defining definition. There are plenty of liquids that are not wet, that don't make you feel wet. Flowing is really more of a property of a fluid, which could be a gas or a liquid. So these are really the specific differences in those different states. So you've either got a fixed volume and shape, right? A solid, if you take it out of it, whatever container you put it in, it keeps its shape. A liquid, you can have a certain volume, but then it'll take the shape of whatever container it's in. And a gas doesn't have a fixed volume or shape. A gas assumes the volume of its container. If you fill a 1 liter beaker with air, like an empty 1 liter beaker, that air is 1 liter of air. And even if you pressurize that, so there's actually more mass of air, it still takes up 1 liter. So the gas is always going to have the volume of its container. It doesn't have its own fixed volume. And then on a molecular level, this is how we might distinguish those states. So solid is going to be packed tightly together. Liquid is going to be close and associated, and it's going to have forces among the particles. We'll get into those forces in a bit. And then gas is going to have no effective attractions or repulsions between particles. They'll be far apart, not associating at all. right? And then mostly, we're going to have mixtures. We're going to talk a little bit about pure compounds and elements and things like that, but primarily what we deal with on a day-to-day basis is mixtures. We're going to look at two different types of mixtures: homogeneous mixtures and heterogeneous mixtures. Which one do you think goes where, based on those two definitions? What is a homogeneous mixture? What is a heterogeneous mixture?
Homogeneous would be the first.
Yeah. So somebody give me an example of one of those. Anything. Doesn't have to be chemical in nature, just anything that you can think of that would fit one of those definitions. Yeah, pizza, right? You said? Yeah. So pizza. Pizza would be heterogeneous because it's a mixture of cheese and pepperoni and whatever else you like on your pizza, but you definitely see all the different parts.
Salt water.
So what would salt water be? Yeah, we might call salt water. Homogeneous. Kind of depends on what happens. Baking soda actually can dissolve in water. So if it's dissolved, it would be homo because it would just look like a clear solution. If it were kind of sitting on the bottom, it would be hetero because you'd see it on the bottom, right? But chocolate?
Chalk.
Oh, chalk. Chalk is actually, well, I don't actually know what's in chalk. Is it just one compound or is it a mixture of stuff? I guess it's got to be a mixture because of colors and stuff like that, right? So that would be homogeneous because you can't tell the different parts of the chalk, right?
Chalk in water.
Oh, chalk in water. Oh yeah, absolutely. That would be heterogeneous because the chalk doesn't dissolve in water. Yeah. What about coffee? What? Why would it be homogeneous?
Because you can't really tell the difference. You have sugar and not.
Right. So if you add sugar or milk or whatever, even just the coffee itself is a whole different, flavor compounds, color compounds, caffeine. So that would all be a homogeneous mixture. You can see the same amount. Right. You'll see the difference in the color, but you won't be able to say the cream is here and the coffee part is over here, right? It'll be the same throughout. So that would be considered a homogeneous mixture. But maybe if you took some coffee and then you, well, coffee's kind of hard to see through. Let's say tea, because that would work, right? What would tea be? Also homogeneous, probably? Nice and light colored, so you can see it. And then if you put something in there, what could you put in tea to make a heterogeneous mixture?
A lot of sugar, marble.
Yeah, maybe too much sugar, so it sits on the bottom, a marble, maybe poop in it, and there's a big piece of poop in the bottom of your tea. That would be heterogeneous. Don't poop in your tea, by the way. I don't know. Another way we can talk about this is how we separate these things. So a mixture can always be separated by physical means, whereas a pure substance can only be separated by chemical means, if it can be separated at all. So here are some examples of physical processes. Somebody tell me what any of these are. Have you ever heard of any of these? We'll be doing some of them in lab this semester. Somebody tell me what one of those are? One of those is? Yeah. Yeah, when a substance goes directly from a solid to a gas. So sometimes that's a way to separate things because one of the components will leave and become a gas and other stuff will be left behind. Anybody give me an example of sublimation? Where might we see that? What? Dry ice would be a good example. That's solid CO2, and then you see all the kind of smoke coming off of it. That turns direct. We never see a liquid CO2. We never see it melt. Although we should note that like smoke that you see coming off the dry ice is not CO2 gas. CO2 gas is colorless. That's actually condensation from the air condensing on the cold gas and making essentially steam, condensed water. But anyway, so that's a good example. Another good example is in your freezer. I don't know if you've ever noticed this, but if you put stuff in the freezer, it dries out over time. You ever put like a uncovered something in the freezer and then it gets all like freezer burned and gross on the outside and gets all kind of dry? That's actually sublimation as well. The water is going from a solid phase, the frozen solid phase, to a gas phase and escaping. Because the water will never become a liquid in the freezer, right? It's too cold. So if the water is escaping, it's because it's turning directly into the gas. So that happens a bit as well. What about some of these other ones? What's distillation? It's a way of purifying, so it's a way of separating things by boiling point. You take a mixture of liquids, you boil them very carefully, and then condense them and collect the different liquids. So the ones with lower boiling points will boil first, you can collect that, and then ones with higher boiling points will boil later, and you collect those later. So that's something like distilled water. The water is evaporated and then condensed, and all the other junk that's in the water, the ions, the whatever other chemicals are left behind, only the water is collected on the other side of the distillation. It's also how things like alcoholic drinks, liquors, and things like that are made. You take a relatively low alcohol thing that's made by yeast, and then you distill it and you concentrate the alcohol. So you end up with just the alcohol, and then you mix other stuff in too. So that's a measure, that's an example of physically separating something. You haven't changed any chemicals. When you distill water, you don't break up the hydrogen and oxygen. You simply take the water from one state, turn it into another state, move it over here, and then recollect it. So those are physical changes. Anybody ever heard of chromatography? Maybe, like it kind of sounds familiar. Chromatography is another way of separating things where you pass a mixture of chemicals over some kind of a substrate, like a piece of paper or silica, which is a chemical. Sometimes you put it through a special tube that's filled with a particular compound, and some chemicals stick to that stuff better than others. A good example of that is if you've ever put some ink on a piece of paper and then it gets wet and the ink kind of like all spreads out and you can see all the different little colors in the ink. That's an example of chromatography, because some of those inks are sticking to the paper more than others, and so they end up kind of spreading out, being carried out by the water. And then finally, what's filtration? Yeah, separating solids from liquids. That's another physical means of separation, where you pour something through a filter paper and the solids stay up on top and the liquid drips down into the bottom. So you've separated those. Again, all of these, you're not changing any chemical components, you're simply separating one from the other. So let's look at, I'm going to skip down here to this table that comes from the book. We can think about this as sort of a tree where we've got all matter that we can put into two categories. It's either a pure substance or it's a mixture. If it's a pure substance, it doesn't have variable composition. It's all the same all the way through. If it's a mixture, it's not. So even a homogeneous mixture, if you get down to the molecular scale, it's not the same stuff, it's not the same composition all the way through. It's got different kinds of molecules in it, different kinds of compounds, whatever. And then those can be separated into two further categories. The pure substance can either be an element, which is a pure element that has no other elements with it. And it means it cannot be separated into simpler substances. So you see here, separable into simpler substances. An element cannot be. It's true that an element can be broken up through a nuclear reaction, but it can't be separated chemically into simpler substances. That's it. That's the basic thing. That example is helium in a blimp, by the way. The other type of a pure substance is a compound. A compound is made up of multiple elements chemically bound together. An example of that would be water, pure water. Same composition throughout. It's made of only one type of molecule, but it can be broken down further if you do chemistry on that water. You can break it down into hydrogen and oxygen. But all those physical means of separation, distillation, filtration, all that kind of stuff, cannot break up the water. When you boil water, it does not turn into hydrogen gas and oxygen gas. It simply turns into water. It simply stays water. The water molecules just separate from each other. So then on the other side, we've got the mixtures that we just talked about. The heterogeneous mixture, which they say is wet sand, where you've got water molecules, and then you've got sand, and they're kind of, you can see the sand, you can see the water. And then a homogeneous mixture, something like tea with sugar, where you've got mostly water, but then these color and flavor molecules, caffeine, and then sugar molecules all in there, and you can't pick out particular domains where here's where the sugar is and here's where the tea is, assuming it's all dissolved. So you should be able to classify things in here. Some of these get a little bit questionable, I guess I would say. And so if I ask you about these on an exam or a quiz, I'm either going to make it pretty clear and pretty obvious, or I'm going to ask you to explain your answer. So one that always comes up, I think it's asked in the book, it's not down here, is it? Is blood. Have you ever seen blood before? Maybe, yeah. Hopefully not too much, but maybe. Where would you classify blood? Well, first of all, let's classify it as either a pure substance or a mixture. So is it a pure substance or is it a mixture?
Mixture.
Certainly a mixture. It's got all kinds of different stuff in there. You got liquid, you got water, you've got blood cells, you've got dissolved compounds, you've got gases, all kinds of stuff. So that's certainly a mixture. So then would you call it a heterogeneous mixture or a homogeneous mixture?
Because sometimes you can see like the plasmids separate from the blood if it's like
Right.
else.
Right, so it can start to kind of coagulate. You can see the different parts. You said homogeneous. Why homogeneous?
You can't see like the iron or something.
Yeah.
It's like,
Yeah, so blood really kind of fits into either category depending on how closely you're looking at it and what you're looking at. If, I just kind of like cut my hand off and blood is spraying across the room, it's going to look pretty homogeneous, right? So it's going to look like red stuff spraying across the room. But if we got really close in and we really looked at it, maybe we could see where it was a little more watery, where it was a little coagulated from some of the proteins and some of the blood cells. If we looked at it under a microscope, which is not the molecular level by far, right? That's still kind of the visible level. But you look at blood under a microscope, it certainly looks heterogeneous because you can see the individual blood cells and stuff like that. So the answer is, well, it depends. Depends how you look at it and what you're looking at. And so if I asked you, like on an exam, where does blood fit? If I just made that a multiple choice question, that would be mean and not a good question because clearly it could go either way. If I asked you on an exam, it would be an open-ended question and I'd ask you to justify your answer, and either one would be correct as long as you had some appropriate reasons for it. Does that make sense? Okay. All right, let's look at some of the ways that your book asks about this particular topic. So look at number 37 here. Classify each substance as a pure substance or a mixture. If it's a mixture, then call it homogeneous or heterogeneous. So first, sweat. Anybody ever sweated before? Is that going to be a pure substance or a mixture? Probably a mixture. How do you know? Yeah, you know at least it's salty and it's probably got some other stuff in there too. Some like odor chemicals sometimes. So is it going to be a homogeneous mixture or a heterogeneous mixture? Really homogeneous. It just looks like water, right? It doesn't really, you can't say, oh, here's the salt part and here's the liquid part. Good. What about carbon dioxide? How do you know it's a pure substance? It's a compound. Yeah, it's made of carbon and oxygen chemically bound together. You can't separate carbon dioxide into other things without actually chemically breaking it down. Aluminum, pure substance, and what kind of a pure substance? That's an element. So a sample of pure aluminum is going to only have one type of atom, aluminum atoms. That's it. And what about vegetable soup? Yeah, a heterogeneous mixture, right? Because you can see all the different vegetables. I suppose unless it's blended vegetable soup, if it was blended up and it would just be homogeneous. But maybe they should be more specific. So that's how we would look at things like that. Okay, so that takes us through chapter 1. Let's look at. So we've talked about some significant figures. We've talked about some unit conversions and some density and classification of matter. And that'll kind of be the main things from that. Hopefully almost all of that was review for you, so you can go through and practice some of those questions, get a little bit better at it as we move on. So let's take like a 15-minute break, and then we will come back. We'll come back at 12:30 and start talking about atoms and molecules. Oh, and actually I need to get my notes. What are we posting?
Professor,
Yeah.
Did you say that the notebook, it's a requirement, right? The
Yeah.
lab notebook?
Mhm.
Okay. And then is there any like places to get them, like besides this hardware store?
Yeah, I mean, there's.
Because like over there, like the ones they have, it has like 100 pages, and like I know we were only gonna use like maybe like what 10?
No, we'll probably use.
Isn't it just for the lab?
Yeah, but you'll probably, with all the questions and everything,
okay.
you'll probably use at least 4 or 5 pages per lab.
Okay.
So
Alright, then
you
it's
won't
like-
use all of it, but
If they're like
I don't
the
know if you
same
can really
price,
find-
like everywhere, then I'll just get it from here.
we can look if there's smaller ones on Amazon or something. You can use anything with what's called carbonless.
Just any like carbon paper.
No, carbonless lab
Oh.
notebook. But they're all
All like
basically the same.
Okay. That's fine.
You can get some with 50 pages instead of 100, but they're all the same price.
Okay. That's fine. I'll just get it from here.
Yeah.
Okay, thanks.
this one, are you gonna be particular about how many significant items?
Yeah.
So.
Well, it depends on the measurement. So you have to see, based on the scale of the graduated cylinder, how much can you measure? Like what precision can you measure?
Okay.
And then for the balances, just make sure to always write down all of the, don't ever truncate off a decimal
Yeah.
place from
Okay.
measurement. Yeah.
Thank you. Yeah. Okay, thank you.
It's like this, you even do shit like you where you just like, just chill and get some, get some lunches. Like, you know, I can get it to do an hour or two. I can get some shit. Try to stay. So I think this.
All right. So I just realized I grabbed the wrong notes on here, so I'll get the right ones. Okay, I think I have the right thing now here.
Did you record the
No. Well, the audio, yes, but the screen was not going. All right. Let's move on here. So this, I'm going to go very quickly through this stuff because not that it isn't important, but it's just kind of a story of where all this stuff came from. And this is the time where I would say an exception to don't read the book. If you're interested in this, if you're at all interested in the history of science or where these things come from, it's definitely a good read in chapter 2 there about how these sorts of ideas came up. So we're talking a long time ago, 1780s, starting to think about this idea of mass and matter as a particular constant thing that doesn't change really. So you have the law of conservation of mass, just saying mass is neither created nor destroyed. That was kind of a big deal at the time because it was thought that, like, for instance, when you burn something, that it was simply gone. It had disappeared, it had turned into energy. If you burn a log, the log is no longer there, therefore the log is has disappeared into the world and as no longer exists. We know that's not the case. What happens when you burn a log? It makes what? Makes smoke. Turns into ash. But even if you burn it so completely that there's no ash, you're still making carbon dioxide and water. Right? You completely combust something, you're still making carbon dioxide. So they didn't see that at first, so they didn't think anything was happening, and then started to realize that, oh wait, actually stuff does continue to exist. So it comes to this idea that matter is not created or destroyed. Then of course later, in the 1900s, we start to realize, well, we actually can destroy matter. How do we destroy matter? Yeah, in nuclear reactions, we can destroy matter. So it turned into energy. That is different, right? So all that needs to be changed in the law is to add on in a chemical process, right? Chemical processes, rather than in nuclear processes. So we still cannot create or destroy matter in a chemical reaction or chemical process. So the next bit is talking about these proportions. So it started to be, there started to be this issue of, like, what is matter made of? And we didn't have atomic theory yet. We didn't have this idea that there were these atoms. So it was this idea, so the ideas were like, well, this kind of a thing is totally different from this kind of a thing. And when we do chemistry, it's almost like magic. It's like we're turning this into this. And there wasn't this idea of rearranging the atoms until we start to think about elements in the 1800s, the early 1800s, and they start to see that, well, when we make these different compounds using the same kinds of elements, they always combine in these whole number ratios. whole number ratios, meaning like, you always have kind of 4 to 5 or 3 to 8 or something like that of these different quantities. So there are some examples in the book of how this works. I'm not going to really ask you to do these types of calculations, but I do want to show you what something would look like. So I'm just going to pull up this example from the book that is not there, that is here. This is on page 49. So a problem like this, and you might be asked to do some of these in the homework. I don't focus on this. We'll get into the math calculations later, so don't worry too much about these kinds of things. But you say you have some carbon dioxide, and you decompose it into the elements, into some carbon and some oxygen. And one sample, you get 25.6 grams of oxygen and 9.6 grams of carbon. The other sample, you get 21.6 grams of oxygen and 8.1 grams of carbon. And the law of definite proportions means that no matter what you do, any sample, you're always going to get the same ratio of oxygen to carbon when you break down that carbon dioxide. And that, it's almost hard to understand because it almost seems just too obvious to us. Like, of course, because we're always going to get the same. If it's carbon dioxide, it's CO2. So of course, if you break it down, it's always going to have the same ratio. But that was not the case then. That was not obvious. If you had some carbon dioxide from burning some wood, and then you had some carbon dioxide from burning some animal, and then you had some carbon dioxide from the next town over, it was not clear that those should actually be the same thing. So the law of definite proportions said, no, carbon dioxide is always this thing, and it's always made up of this much carbon and this much oxygen, and it's always the same. And if you change the amount of carbon or oxygen, you get a different material, and that has its own ratios that stay the same. So that's the idea of definite proportions. The proportions don't change with different samples. And then to make it even a little bit more careful, and this really is what led to atomic theory, is this law of multiple proportions. So you have two elements that form a series of compounds. That's, for example, well, let's use carbon again, for example. You have CO, which is carbon monoxide. You have CO2, which is carbon dioxide. They would have known that there were two different kinds of gases. Maybe not with those, maybe with nitrogen, because then you could have different colors. Let's use nitrogen. That's a better example. There's more of them. So you've got all kinds of different gases that can be made from nitrogen. You've got N2O, which is nitrous oxide. You've got NO2, which is nitrogen dioxide. You've got NO, nitrogen monoxide. You've got N2O5, dinitrogen pentoxide. These all have different properties. Some are poisonous, some are not. One is laughing gas, right? One of them is brown. And all of these things are made from nitrogen and oxygen. And they found out that if you do this, like breaking it down into nitrogen and oxygen, you always get these whole number proportions that we just mentioned, which was kind of a striking thing. You'd think that this one would just have like some nitrogen and this one would have some oxygen, and maybe this one had more oxygen. But it was always like whole numbers, like 1 more oxygen or 2 more oxygen or 2 more nitrogen. And so from that, they were able to deduce, well, wait, this thing must be made of these little individual particles, because if they're particles, you can only count them, 1, 2, 3, 4, 5. If it was just some stuff, which was what was thought at the time, some kind of, who knows, kind of magical stuff, then you should be able to take proportions, that you should be able to take like little tiny parts of it. So that's the idea of multiple proportions. And we're not going to go through multiple proportions problems. Again, you can look at those in the book. I'm not even going to go through one now. But you can go through these problems like they did, where you can look at the different proportions and find that they reduce to these whole numbers. We'll get into that a little bit when we get into percent composition and elemental composition at the end of the chapter. But for now, we'll leave it there. All right. So then from there, we get atomic theory. Atomic theory obviously is a big deal because we still know that it's correct today. So 200 years later, we can actually see atoms using certain types of techniques. We have things like atomic force microscopy. Anybody know what that is? Have you ever used atomic force microscopy? You can drag a tiny little tip across a surface and actually watch it kind of bouncing off each atom. So you can get a picture of each atom. We actually have one of these at Harper. And you can see this thing. And the 200 years ago, more than 200 years ago now, this theory was developed based on these observations. And now it's actually really confirmed. And based on our definitions, remember on Tuesday, that is still a theory because it explains a lot of things. It explains the way that matter interacts with each other. But it's a very, very, very well proven theory now, right? We pretty much accept it completely. I'm sure you can find some people who don't believe that things are made of atoms, but I imagine they're few and far between. Okay, so here's atomic theory. Stuff's made up of atoms. In a given element, the atoms are the same. The atoms of different elements are different somehow. Now we know what that somehow is. What's the somehow? What? Yeah, protons, neutrons, electrons. Protons particularly. When the atoms, they didn't know that then. They just knew that there was some difference. When different atoms come together, you make a compound, and the compounds are always whole numbers of elements, or whole number ratios, because you can't have like carbon and then half of an oxygen atom. And then when we do chemical reactions, you're not magically turning some kind of unknown thing into some other unknown thing. You're taking the atoms apart and you're rearranging them into new things. And that's really the big consequence of this. That when we do these transformations, these amazing transformations that at the time were like magic, we're really just taking atoms apart and putting them back together in different ways. And then that allows us to explain all these different observations, all these laws, multiple proportions, definite proportions, conservation of mass. The theory explains those laws because it says, well, if you think of things as made of atoms, then that rearrangement of atoms is what does that. Okay. Okay. We'll get into some of this other stuff later. I don't want to get too much into all of this. These will all be posted, by the way, so you have to write down all these words. But I do want to show you a couple of the early experiments that then went further to try to figure out what are these atom things? What is the point of this? And what are they made out of? So this is something called a cathode ray tube. Has anybody seen one of these before? Yeah, where might of you have seen that?
We had one in school.
Okay. So where might you see these in just like common things that you have in your house? You may or may not have one of these in your house anymore, but old TVs. Do you remember TVs and computer monitors used to be like fat before they were thin? Is that familiar? Yeah. So that thing, that's a cathode ray tube. And what that is it's a little sample of some kind of metal usually. And you put some power across this metal and it releases electrons, actually shoots electrons off of it. You use magnets to control where the electron goes, because it's a negatively charged particle. And then when the electron hits the end, it hits a type of material that glows when it gets hit by an electron called a phosphor. So the electron hits the thing, it glows, and the magnets make it go scan back and forth. You ever tried to take a video of an old TV and you can see the lines like moving down it, or a really old computer monitor where you can kind of see that? That's what's happening. The cathode ray tube is being directed up and down the TV over and over again. And the phosphor is glowing, which is why the images remain. So when this was first developed, they didn't know that that was a thing, that was a particle. They called it a cathode ray because they thought it was a ray, like a ray of light, because it sort of behaved like a ray of light. But then they noticed that it could be diverted by magnets. And so if it could be diverted by magnets, it must actually have a charge to it. It must be a charged particle. And that was the development of the electron. The idea that there is this electron, that atoms have these electron things, and that if we put enough energy into that compound, we can release the electron, shoot it off, and then control it and do stuff with it. So that's how we know about electrons. And that they had charge and all this stuff. So the next thing is, do I have a picture of this one? Yeah. So we knew atoms overall were neutral. So if you had these negatively charged particles, you must also have positively charged particles, right? And so that was developed, and the idea of protons and stuff was developed. And that was what was called the plum pudding model, which is right here. You can see this little picture. What was thought was that you had these kind of clouds, these atoms that were made up of electrons, and then protons were distributed evenly throughout, like plums in a plum pudding, is the idea. The protons were distributed throughout the whole atom. But then they did this really cool experiment called the gold foil experiment, and it showed actually something else. Anybody know what this showed without reading everything? What is actually the structure of the atom? If the protons are not distributed throughout the whole atom, where are they? The what? Somebody said it, no? In the nucleus, in the middle. So what they did was they took a radioactive sample that shot out these alpha particles, and we'll talk about what those are, but they're just basically massive particles. We'll get into that in, actually, that's next semester, nuclear chemistry. But they'll shoot out these alpha particles, and they shot them at some gold foil. So if this was Rutherford was the scientist's name who did this. Ernest Rutherford in 1911. So if it's a plum pudding model like this, you would expect that these big heavy particles would pretty much just go through the atoms. But they didn't. What they did was they got deflected. So some of them would go through, but most of them would get deflected either a little bit or a lot. And alpha particles are big and heavy. They were one of the heaviest particles that we knew about on that scale. And it was really hard to get them to see these deflections. So most of the deflections were going through or slightly diverted, but some of them were really major deflections. And if that were the case, that must mean that there is some really big thing in there, in this gold foil, and that really big thing is the nucleus. So instead of the heavy protons and neutrons being distributed through the atom, they found, no, actually they're all concentrated right in the center. And that was the development of this idea that there is a nucleus, and then there are electrons around the nucleus. Okay, so let's look at what we know about now. We know that we have a nucleus in the center made of protons with positive charges and neutrons with no charge. And then we have electrons around the outside. And we'll talk about where the electrons go and the structure and all that stuff in a couple chapters, I think. But this is really the most striking thing about this to me. The nucleus itself is about 10 to the minus 14th meters. That's tiny. The size of the entire atom is 10 to the minus 10th meters. Still tiny, but think about what that means. That's, every scientific notation is 10 times, right? So the size of the atom is 10 times 10 times 10 times 10, which is what, 10,000? 10,000 times bigger than the nucleus. That means that 10,000 times the distance. Think about where we are. Let's look at a meter, right? Think about a meter right here. And then think about 10,000 times that. What's 10,000 times that? That's 10 kilometers. That's about 6 miles away. So if we were the nucleus right here, if this were the nucleus, the electrons would be 6 miles away. And all that would be between us and them is empty space, nothingness. So most of an atom, the vast majority of the space of an atom is simply nothing. Which means the vast majority of all matter, whether it's a book or a table or whatever, is simply nothingness. It's just space. And I think that's kind of interesting and frightening at the same time. That most of what, we're standing on this floor, but our shoes and the floor is mostly nothing. All right. So now we know some things about these subatomic particles. You can look at a table like this in the book. This is actually how much they weigh in kilograms. So these are really messy, tiny, tiny numbers. We don't really want to use them a lot because they're kind of messy. So we usually talk about the weight of atoms and the weight of the particles in another unit called atomic mass units. Those are basically defined as 1/12 of the mass of a carbon atom with 6 protons and 6 neutrons, so that a proton ends up being approximately 1 atomic mass unit, a neutron approximately 1, and electrons are extremely light. They pretty much don't even contribute to the mass of an atom, which is why we talk about atomic mass as being the sum of the protons and the neutrons. All right, so that was a lot. Is that okay? Sort of got the idea? I think the story and the history is interesting, but I want you to just focus on what we know now, the modern picture of the atom, what that is. Okay, so let's move on and talk about that. Sure, we can save that. Okay, so let's talk about how we count these things. And again, this is probably stuff that you've heard before. Let's look at a calcium atom. Atoms of calcium, we've got 20 protons, and then you must have 20 electrons. We can always find the number of protons and the number of electrons in a neutral atom by looking at the periodic table. So calcium is atomic number of 20. That tells us it's got 20 protons. And then a neutral calcium atom has 20 electrons. How do we know how many neutrons it has? We can look at the atomic mass minus the protons, kind of. So that sort of works. But what we're going to focus on here is what we call the mass number, because the number of neutrons in a nucleus can differ. There can be different numbers of neutrons in different calcium atoms. Anybody know what that word is? Isotopes, right. Isotopes have the same number of protons, but different numbers of neutrons. Now, let me ask you this. If that's true, it is true, and protons weigh about 1, and neutrons weigh about 1 atomic mass unit, then how come the atomic masses on the periodic table, those red numbers, are all kinds of crazy fractions? Yeah.
Because it's the average.
Yeah, so those masses are actually averages of all the common isotopes. They're weighted averages of the isotopes. So let's look at some different isotopes and how we identify them. All right. So that means that an isotope of calcium might have a mass of 40. And we would write it like this. We'd write the element symbol, and then the 20 down here for the protons, and the 40 up on top left for the atomic mass, or the mass number. But that's one specific calcium atom. So if I said, because I do say this and people get it wrong, if I say what is the mass number of an atom that with that symbol, calcium 40, the mass is 40. It's exactly 40. It's not 40.078. That number up there is an average of different isotopes. So let's look at some of those. Bromine. Oh, I think I'm running out of memory here. Let's see. It's not too bad. Not great. So bromine, element Br, number 35. Bromine has 35 protons. The two common isotopes of bromine are bromine 79 and bromine 81. We would put a 35 in the lower left-hand corner, but that's redundant because if it's bromine, we know it's 35. It's got to be. Anything else is not bromine anymore. So what is the mass? What is the atomic mass of bromine on the periodic table? You see it? 79.9. There isn't even an isotope of bromine that's 79.9. There's not even an isotope that's 80. So what's going on there? Yeah, there's approximately a 50-50 distribution of these two isotopes of bromine in nature. And so when you average 79 and 81, you get in the middle, which is about 80, which is what we see on the periodic table. Okay. Other elements have different kinds of abundances. Carbon, for instance, remember the whole atomic mass unit is based on carbon. So carbon 12 weighs exactly 12. But on the periodic table, it's 12.011. So why is that? What other isotopes would you expect to find of carbon? Yeah, carbon 13 and carbon 14 are the common ones. So carbon 12 is about 99% of the carbon in the world, and carbon 13 is a little less than 1%, and carbon 14 is around 0.1%. So you have that distribution, you average those, and you end up with a little bit more than 12 when you average them all together. And that's where those numbers come from. All right. So let's look at some ways that we can draw some molecules and some ions. We're going to get into some chemical bonds, and we'll talk in detail about different ways to do this. But for now, we're going to focus on we're going to look at different ways to draw these things. So when we look at these different kinds of molecules, we're talking about covalent bonds, which are sharing electrons. What's another type of bond that we'll get into later? Ionic is another type of interaction. So a covalent bond talks about sharing electrons. And so a structural formula of a molecule would be where we show how the electrons are being shared. And when we get into drawing what we call Lewis structures, we'll get into how we do that and how we make sure they're connected in the right way and all that. We'll get into that later in the semester. But you may see things like this. Have you seen types of pictures like this before? Probably. Yeah. And so all that is just showing that here is how these things are possibly arranged. And this is like sharing 2 electrons. Sometimes these are drawn so that it reflects the shape, and sometimes they're not. You may know from previous chemistry that that's not the shape of water. It's not in a straight line like that. What does it look like? Maybe kind of want to make it a little, yeah, it's kind of like a bent structure, right? We'll get into why that is later. But you could still make, this could still be an appropriate structural formula because it shows how things are connected. Just depends on what you're trying to show. So here are some other ways you might see molecules represented. A molecular formula is going to tell us the number of atoms in the molecule of each type of atom and what types of atoms are actually in there. And then you've got a structural formula, which, like we said, shows the connectivity. A ball and stick model is giving a little more information. That usually gives you the shape, the 3-dimensional shape. And then what's this crazy space filling model? What does that mean? You seen that before? Maybe? No? Why would we have that? What is that? Why do we make everything big blobs? Get rid of the lines. What's the point of that?
Easier to draw.
Easier to draw, really?
Well, I mean, like when you're making like one of those pictures,
Yeah.
you don't want to make like a bunch of the letters.
Okay, so maybe you don't want to make a bunch of the letters. But this could also be really tricky to draw, right? Because you have to get all the angles right and the spheres put together. I don't know. Maybe it's easier. Yeah.
It seems more accurate because instead of a line representing electrons, like the electron clouds are actually going through each other.
Yeah, so the space filling model more accurately reflects reality. In reality, there are no lines. There are no, it's not like the hydrogen atom is here, the carbon atom is here, and then there's some like line in the middle where they share their electrons. Each atom is approximately a sphere, and they sort of mash together so that their clouds can be close enough for the electrons to be in both of them. So a space filling model is a more accurate representation of what that molecule is actually looking like on that scale. That's what it would look like. So when we care about the overall shape of a molecule or what it looks like or how well it fits in a particular spot, space filling models can be really useful. A lot of this is used in things like drug development, drug design. When you want to build a new molecule to, let's say, fight, well, like HIV or AIDS is a good example. That virus has particular proteins and enzymes that do the things that it does to hurt people. And so we design drugs to fit in these particular proteins and sort of take them up so they can't do their job. And to do that, we have to look at space-filling models very, very carefully with very fancy calculations and try to figure out what kind of a molecule might fit in there. And that's how we might design a molecule and then build it in the lab and then test it and see if it actually does that. So that's where we might see that. Okay. So ionic bond is the next thing we're going to talk about. And I think it's kind of a bad name. Not like it's a swear word or something, but just that it's not super accurate about what that really means. The reason I don't like it is because of the term bond. In an ionic bond, the molecules aren't really doing anything to each other. They're simply attracted to each other through electronic forces. We know positive and negative attract. So ions are either positively or negatively charged particles that simply attract each other and kind of hang out together. That means that we don't draw a line for an ionic bond, because that line has a very specific meaning of sharing electrons. And an ionic interaction is not sharing electrons. It's just a positive thing and a negative thing hanging out by each other because they want to. So it is not correct to go like that. NaCl, sodium chloride, that's an ionic interaction of sodium and chloride ions. But that is not a covalent interaction. Those electrons are not shared. It's simply positively charged sodiums and negatively charged chlorines being sort of close to each other. And we'll get into what that particular structure is in a little bit. Whoops, I hit the wrong thing. Let's try that again. All right, I don't know what I did in my notes, but that's okay. Okay, so let's look at some examples. Let's look at potassium. Okay, that's number 19. How many protons does potassium have? One atom of potassium. How many protons? 19, right. How many electrons? Also 19, because that atom is neutral. It has no charge, which means the positive protons and the negative electrons must balance out. How many neutrons does it have? Good, nobody answers. It's a trick question, because I didn't tell you which isotope of potassium it is, so we don't know how many neutrons it has. If I said it was potassium 39, then you could tell me, but I didn't say. So then you could tell me it had 20 neutrons, but I didn't say that. So. Okay, if you lose one electron from a potassium atom, what do you get? We still have 19 protons, but we lost an electron, so now we have 18 electrons. Another way to write that is in a chemical equation. We could say a K atom becomes a lost electron plus a charged potassium ion. Okay. So now that we have more protons, which are positively charged, than electrons, we have an overall positive charge, +1 charge. And so that's not an atom anymore, that's an ion. That's called a potassium ion or cation. We have a couple words for that. Probably heard these before, but a cation is a positively charged ion. What's a negatively charged ion? It says right there. Anion, right? So we make ions, we make charged particles by losing or gaining electrons. How might we do that with an anion, though? What do you think? How do you think we make a chloride ion, a chloride anion? Where do you think that comes from? What neutral element would a chloride anion come from? Chlorine, yeah. So we could take a chlorine atom that has how many protons? 17. And how many electrons? 17. We can add an electron to it, and we end up with a chloride ion, which now has how many protons? Still 17. And how many electrons? 18. So one more electron here. And that's what we call a chloride ion. Another thing that we can say about these, let's do that count. So this chlorine has 17 protons and 17 electrons. And this chloride has 17 protons and 18 electrons. So we could say that chloride ion and potassium ion are isoelectronic. Iso means the same. It's a prefix that means the same. So isoelectronic means the same number of electrons. Cl minus and K plus both have 18 electrons, and that makes them isoelectronic. Okay, let's look at some different examples. So we talked before about, I think it was in that pretest, about how electrons are responsible for all the behavior of all the atoms. So it's always really important to know how many electrons you have in any given atom or ion. So I'm going to list some ions, and I want you to come up with how many electrons are in there. And then I want you to, well, then we'll do one more thing. So the ions that you're going to look at are these. So here are 5 different ions. When we have that extra number up there, that more than just 1 plus, that means that more electrons are being added or taken away. So I want you to write down how many electrons each of these ions has. And then I want you to answer the question, which of these are isoelectronic? So I'll give you a couple minutes to do that. Okay, got some numbers? Yes? No? Maybe? Okay. What do you got for this one? How many electrons? Oh, I keep forgetting you can't see my pen on these new things. Okay. Yeah, the first one. 18 electrons. What about this one? 18. What about this one? And this one? Okay, everybody agrees? Anybody get anything different? What do you think? Should it be 42 or 36? You're wrong?
Yeah.
You're gonna change your answer? Yeah. So it's got to be 36 because it starts at 39 at the neutral atom, and then if it's 3 plus, that means it's lost 3 electrons to become more positive. So 39 minus 3 is 36. Okay, so which are isoelectronic? Yeah, the first two and the last two. The first two and the last two are isoelectronic. All right, feel good about that? You can probably do that. There's sort of a shortcut to this, which is looking at the periodic table. Let's look at some of these elements which you've just been doing, but notice some of these elements on the periodic table. For instance, sodium is right here, chlorine is right here. Sodium becomes sodium plus, chlorine becomes chloride, 1 minus. What do you think that has to do with where things are on the periodic table? Want to make any generalizations? No? Nobody wants to? We can actually learn some things about common ions that are formed based on the periodic table. And when we talk about electron orbitals in a few chapters, we'll get into why that is. But one thing that we can say is that all of these in this first column tend to make +1 ions. And all of these in the second column tend to make +2 ions. Any others that you know about that you might be able to generalize? Actually, to be totally correct here, let's cut that back a little bit. It's not exactly all of them, but all the common ones that we really care about. We'll do that. And then over here, those 3 are generally -1, and these are generally -2. There's a couple more that we can generalize, but for now, we'll leave that there. When we get into the naming and the ions, things like that. But that's a nice shorthand to know what kind of ions you can make. So you don't even necessarily have to count things all the time. You can just know that that first column is always going to be +1. The second column is going to be +2 when they make ions. All right, so I'd like to talk a little bit. I want to show you something about what happens when you change atoms to ions. So has anybody here ever seen sodium metal? You seen it? What does it look like? Silvery. It's a metal. But when we think about sodium, we don't usually think about metal, right? We usually think about salt, which is sodium chloride. And that's what does that look like? Have you ever seen salt? It's kind of like whitish. It's actually clear if it's pure enough, but it's really hard, brittle. It's not really metallic at all. So sodium is this soft metallic solid, and chlorine is a greenish poisonous gas. But then you make sodium ions and chloride ions, and you get something very different, right? You get sodium chloride, which is salt. So I usually do this, but with these new systems, I don't know if I have enough memory in the computer, but we'll see. Let's look at some sodium metal. Is that running? Oh, it's not going to talk though. Hold on. Oops. We need this as our playback device. Make sure everyone is still recording. Yeah, okay.
Okay, we're rolling.
We're rolling?
Yeah.
So they just threw some sodium in a lake. You can see it sort of buzzing and hissing. That's the sodium right there. It is metallic, but it actually reacts with the air. Yeah, so hopefully they weren't too close. Holy crap, indeed. So the sodium is this metal, but it reacts with the air to make sodium oxide, which is this kind of whitish coating. And then you can actually cut it. You can cut it with a butter knife. It's like a soft, squishy metal. It's almost like Play-Doh. A little harder. It's harder than that, but you can cut it with a dull knife. And you can expose this shiny surface. And so if you take a big chunk of it and you throw it in the lake, which don't do that, obviously, what happens is it starts to react with the water a little bit. And because it's so soft, it melts. As soon as it starts to generate some heat, it starts to melt. And then as it melts, it falls into the water, and all of a sudden, all the surface area is exposed. It reacts with the water, and it forms hydrogen gas, and then the heat ignites the hydrogen gas, and that's the explosion that you see. So sodium metal by itself is a pretty dangerous thing. If you buy it, you can buy it. You can just, I think you can just buy it on Amazon or something. But it's actually shipped in underneath oil. Like it's submerged in oil so that it can't touch air, because once it starts to touch air, it breaks down, it forms that sodium oxide. And if it touches water, you have a massive fire on your hands. In fact, it's a fire that can't even be put out with a standard fire extinguisher. You need a special Class D fire extinguisher because it will react with the CO2 in a traditional fire extinguisher also. So anyway, the point of that is the difference between a metal and an ion is huge, right? Sodium ions are not dangerous. We eat it all the time. That's our salt. Sodium metal explodes when it hits water. Same thing with chlorine. Chlorine gas is a green, poisonous, really dangerous gas. It was used as a chemical weapon in World War I. Chloride ion is another important thing in our body, that we need for various processes, and we eat it all the time. So those little pluses and minuses on the top of things are really important. They completely change the nature of what you're talking about. So if you're like, if we have an exam or something, and you don't put the little plus on the sodium, and you say, well, I meant to put the plus on there, I just forgot. I believe you, but that's a big difference. So now instead of talking about a sodium ion, you're talking about the exploding lake thing. And that's why that's important. Okay. So ions can be simple, like chloride, bromide, sodium, potassium. They can be polyatomic, like these. When we get into naming in chapter 4, you'll see we'll have to know a whole bunch of those. Hopefully you already know them from or chapter 3, actually, next chapter. Hopefully you know them from some of your previous classes. I'm skipping some of this stuff so we can get to the more important problems. This is a device called a mass spectrometer. Anybody ever seen one of these before? Used one before? We have some. We'll get a chance to use them this semester. What this device does is you put some molecules in this machine, and it actually breaks electrons off of them, so it makes ions. And then it separates them by mass. So you can actually get different masses of different molecules in a sample in a mass spectrometer. You can effectively weigh a single molecule in a mass spectrometer device. And so that is how we can actually figure out these masses in these different isotopes. When we look at, I don't have that picture in here, but you can see it in your book. When you look at the mass spectrum of carbon, for instance, you see separate peaks for the different isotopes because the individual atoms are going through at different times. And so this is how we do that weighted average that we just talked about. So carbon is about 98.89% carbon-12, 1.11% carbon-13, and There's actually a little bit of carbon-14 in there too, but not much. So when you take a weighted average, that means you multiply each by its fraction. So we're going to take 0.9889 times 12, 0.0111 times 13, and that's when we get the 12.01 AMU that we see on the periodic table. All right. So we talk about all that stuff, and I said, look, that's not actually the mass of an individual isotope. That's an average mass. But now I'm going to tell you, even though there's not a single carbon atom with a mass of 12.01, they're either 12 or 13 or 14. Even though that's true, when we have some sample of carbon, we can assume that it's made of one type of atom with a mass of 12.01. Why? If I have a jar full of carbon, I can assume that every carbon atom in there has a mass of 12.01, when in reality, none of them have a mass of 12.01. Why is that?
It has the same amount of different types as the average does.
Right. We're talking on such different scales here that we can assume that the average applies to each atom. Are we ever going to count individual carbon atoms? Like, if I told you to go weigh out 4 grams of carbon, would you like count out however many atoms of carbon that is with tiny tweezers? No, it'd be impossible. They're way too small. The only time we would ever actually count atoms is in a mass spectrometer. And we're not usually doing that. So for purposes of our own measurements and our own math and our own calculations and weighing and all that stuff, we can assume the average because there's just so many atoms in there that it's always going to be approximately the average. So that means that we can do calculations like that, like these. So let's talk about the mole. Have you ever heard of this before? You like it? Is it fun? Maybe a little, maybe not. So a mole is defined as the number of carbon atoms in exactly 12 grams of pure carbon-12. How many atoms there are. And what's that number that you need to know now? (6.02 times 10 to the 23rd). Is there a unit on that? Is the mole a measurement? It's not. It's a count, but it's just a number. So it comes from the number of carbon atoms, but you can have a mole of anything. A mole of seconds is a lot. 4 million times the entire existence of the Earth. A mole of marbles would cover the entire surface of the US to a depth of 70 miles. So a mole is not useful for counting larger things, right? A mole is only useful for counting very, very tiny things because it is such a big number. What other numbers do we have words for like a mole?
Pi.
What?
Pi.
Well, pi is a number. That's true also. But yes. So what about for a count though? If we count things. Like a dozen is a good example, right? How many is a dozen? 12. 12. Everyone wants some donuts? Wouldn't that be cool if donuts just like arrived as soon as I said that? I should time that out. Sorry, I'm hungry. It's just. But yeah, so we have a dozen. A dozen is 12. We could have a half a dozen, is 6. We could have 3 dozen, is 36. Now, when the same thing occurs with moles. So we can have a mole, which is 6.02 times 10 to the 23rd. We can have half a mole, 3.01 times 10 to the 23rd. We can have 3 moles, right? We multiply that by 3. 1.8 times 10 to the 24th, and so on. So don't think of it as some specific chemistry thing. It's just a name for a number, a name for a quantity. And it works very well for small things. So we usually use this for atoms or molecules. And we can say that there's that many of them in a mole. And then this relationship based on grams is really important because it allows us to count by weighing. Like we just said, we cannot pick out a certain number of carbon atoms, right? It's just not possible. We don't have tweezers that small, and we wouldn't want to count that many. So we have to count by weighing. Has anyone ever seen one of those things we have to like guess the number of jelly beans in a giant thing in a store, and then you win all the jelly beans or whatever? You know what I'm talking about? So somebody has to figure out who wins, right? So do you think they go through and they count each one to see who won? Probably not. Probably not. So how might you do that instead? How could you figure out how many jelly beans were in a giant jar if you're the person running the competition without actually counting each one?
Weigh it out.
Yeah, you could weigh it. So if you knew how much each jelly bean weighed, and then you know how much the whole thing weighed, and you assume all the jelly beans have the same weight, you just divide, and then you know how many you have. And that's exactly what we do in the lab when we measure things out in grams, but we actually want to count them in molecules or in moles. So let's show how we do that.
They have to subtract the weight of it.
Yeah, you'd have to subtract the weight of the container too, or tear it or something like that, right? Yeah. All right, so given 10 grams of aluminum, how many moles of material are there? And then how many atoms of aluminum are there in this number? So this is what we're doing. We have 10 grams of aluminum, and aluminum atoms are tiny, so that's essentially like a giant jelly bean container filled with jelly beans, but you've got aluminum atoms. We can't possibly count the atoms by looking at them. So we're going to weigh it out, figure out how many moles there are, and then how many atoms there are. And we're going to do this just like we do all these other conversions. We're going to set it up the same way. So we're going to take 10 grams of aluminum, and we're going to multiply that by a relationship that tells us the number of grams of aluminum in a mole of aluminum. And the abbreviation for mole is MOL. It's not a great abbreviation. You just lose one letter. But M was meters and MO is months, so we got to go with MOL. Sorry, that should be AL, aluminum. How do we find a relationship that tells us the number of grams of aluminum in a mole of aluminum? You know? Where can we look something like that up? Yeah, periodic table. Because the mole is defined based on carbon, based on the mass of 12 grams of carbon-12, because that's how it's defined, each of those red numbers tells us how much a mole of one of those elements is going to weigh in grams. So we find aluminum, which is number 13, and we see that underneath there it says 26.981538. We can only really get 3 significant figures here anyway, so we can call that 27.0 grams per each mole. So that periodic table tells us how many grams are in a mole. It essentially tells us those unit factors for doing conversion problems like this. Yeah?
Would you say not to do that until the end? Like not take off significant numbers? Or can you do that in this case?
Yes, so that's true. However, in this case, we can pick how many we want to use from the aluminum. So it doesn't matter. It should give us the same result either way. All right, so now we cancel grams, and we're left with moles. So 10 divided by 27 comes out to about, somewhere, right? .370 moles of aluminum. So 0.37 moles. That's what, about a third, a little more than a third of a mole. We can also always check to make sure that that makes sense. If 27 grams is 1 mole and we have 10 grams, then we can think, all right, well, we got to have like about a third or so, because 10 is about a third of 27. You see that? So if you flipped it and you got some big number like 270, you'd know that was wrong, because if 1 mole was 27 grams, how could 10 grams be 200 and some grams, 270 grams? All right, so we got the number of moles. So now how do we get that second question? How many atoms of aluminum are there? What? Yeah.
Multiply by 6.02.
Yeah, so we're going to do a similar conversion using the other unit factor right here. So that's 0.370 moles times a factor that gives us atoms per mole, and that factor is 6.02 times 10 to the 23rd per each mole. So now we've got moles canceled, and we end up with atoms, and that comes out to 1.53 times 10 to the 19th. And then check that number. Does it make sense? Right? If 1 mole is 6.02 times 10 to the 23rd, we've got a smaller fraction of that. So yeah, that probably makes sense, right? 0.37 times 6.02 times 10 to the 23rd. Oh wait, no, that doesn't make sense. Should be about, that's way less than it should be. So good thing we checked that. Let's try that again. Yeah, it should be about should be the same scale here, 2.23 times 10 to the 23rd atoms of aluminum. So good thing we checked, right? Got to make sure that it makes sense. If it's about a third, it should be about a third. Okay. Dealing with these big numbers can be a little bit tricky, a little bit confusing, especially also if you're typing into calculators. So I want to show you something, if you haven't used this before. Let me flip this and see if we can see it. Can I borrow a calculator? So if you have a calculator like this, does anybody know the easy way? Let's turn the light off so we can see it better. To do like scientific notation stuff with these big numbers. Have you ever seen that? The EE thing? Yeah. If you're doing a calculation like this, just to make sure that you do it right, a nice way to do it, and actually the more basic calculators have this now too. We might do 0.370 times, and rather than do 6.02 times 10 to the 23rd, which sometimes doesn't work out as nicely as it should, just depends on the calculator. Another way to do it is to say 6.02, and then there's this little EE thing right there. Do you see that? So we go 6.02. Hold on, I gotta zoom in. These things are a little clunky. Okay. 6.02 EE, which just puts a little E there, 23. That means 6.02 times 10 to the 23rd. And so then the answer you get, 2.2274 times 10 to E23 means times 10 to the 23rd. If you put that E there, that means you're not going to get messed up with order of operations or anything like that. Thank you. If you haven't used that before, that can be helpful. Okay. All right, so try this next one then. Same question, we're just looking at gold instead of aluminum, and we're looking at milligrams instead of grams. So see if you can figure out how many moles are in that quantity, and then how many atoms are there in that number. All right, got some numbers here yet? Yeah, maybe, no. Well, let me step through it for you. For those of you who weren't sure of where to start here. We'll take that 5.02 milligrams of gold, and in order to use the periodic or the atomic weights, we need grams. So that's going to be our first conversion, is to go from milligrams to grams. How many milligrams are in a gram? 1,000. Then, now that milligrams are canceled, we have grams. We can go grams to moles based on the atomic mass. So we look up gold, AU, which is way down number 79, and that's going to be 197 grams per mole. Okay. So that's going to tell us how many moles are there. 5.02 times, or divided by 1,000, and then divided by 1.9, or divided by 197 gives us 0.000. You got that, right? Is that right? What you got? What would be a better way of expressing that, maybe? Like in scientific notation? A small number? That'd be 2.55 times 10 to the negative 5. Okay. And then we can figure out how many atoms there are also. So we can take 2.55 times 10 to the minus 5th. That would be moles. And then to get moles to atoms, that's when we use Avogadro's number. 6.02 times 10 to the 23rd atoms per mole. Multiply those together, and we should get 1.53 times 10 to the 19th atoms of gold. Is that what you got? Great. Okay. So we've got this many moles and this many atoms. Okay. So again, even though we're using moles and we're talking about some different things here, this is really the same type of a problem that we saw in the last chapter. We can think of it as converting units. We're converting from, in this case, milligrams to grams to moles, and then moles to atoms. It's still just using that factor label, cancel your units thing, just like with density. It's a little bit of a different relationship, molar mass or density, but the procedure is really the same. There's no new types of problems here. We're always going to be doing that same kind of thing. All right, so keep that in mind as you're practicing. And then the final part of that is to talk about the molar mass, which is, again, that formula weight or atomic weight. We can calculate the molar mass of any material, the amount of mass in 1 mole. I guess we should define this. And we can calculate that by adding up the masses of the constituent elements. So we can call it the molecular weight if it's a molecule, molar mass, formula weight. All those terms are interchangeable. And you can practice that. Do I have any here? By calculating some molar masses or molecular weights. So how would we find a molar mass of water? we know we could find a molar mass of a hydrogen atom by looking up there, right? Well, that's the 1. And oxygen is 15.9994. So water is just going to be adding all that stuff together. We've got 2 hydrogens and 1 oxygen. So 2 times 1.01 plus 16.0 is going to give us 18.0 or 18.02. With significant figures with molar masses, it doesn't matter because you can use as many as you want or as few as you want. So if there's no actual measurement in the problem, you can just pick however you want to do it. I picked 3 significant figures for these. You could just pick whole numbers if you like to do it that way. Whatever, it's fine. How about table salt, NaCl? So what you got, 58.5. We should also note the units here. This is going to be grams per 1 mole. Or the other way we would write that is grams per mole. So when we're using this in a conversion factor, just like we did with the individual elements, we got to make sure to have the fractions right, that it's grams per mole. And then you don't have to think about whether you need to divide or multiply as long as you follow the units. If you're canceling whatever you need to cancel, make sure you put that on the bottom, the other thing on top, and then the number always goes with the grams. Okay. So here's some more you can do. Same thing, you just got to multiply by the number of them. Let's try one more. So let's jump down to acetaminophen, which is what we call Tylenol is the brand name. See if you can find the mass of that one. And we'll see how we do on numbers. Have we got a number yet? Yeah. 151. Have we got something different? So how'd you do that? Okay. So yeah, you just multiply like 8 times 12 plus 9 times 1 plus 14 plus 16 times 2, and that should do it. All right? And then you can use those masses in the same types of calculations. So we could talk about 1 mole of acetaminophen or half a mole, and then use that as a number. All right, so that's molar mass. we will get into the periodic table on Tuesday. So we've done it a little bit, but we'll get a little bit more. So we've pretty much finished chapter 2. Not every little bit, because there's a little bit of the periodic table in there, but we've pretty much finished that up. The chapter 2 mastery chemistry homework will go up today. It'll probably be due on Thursday. And then chapter 3 is a little bit longer, so we'll probably take the whole week next week on chapter 3. A lot of naming and then balancing chemical equations and that kind of stuff. So make sure that your labs are due Monday at the beginning of class from the last lab, all your write-ups and calculations. We'll have the next lab on Monday. Then quiz on Tuesday. And yeah, it's going to go fast. Mastery chemistry due Sunday night. So have a great weekend. Work hard, lots of studying, and I'll see you on Monday.